So chemical formulae, equations, and calculations. First things first, equations. Chemical equations, yeah, we keep calling them chemical equations, but equations are of multiple types, and you must first get used to all of those types so that you are able to write them in whatever type the examiners ask you of. Okay, so
Mm.
the first two foremost types are word equations, as said, and symbol equations. Word equations are pretty easy. You just write the name of the reactant and you give an arrowhead, which we call gives us. Okay, you're not going to pronounce arrow when you're going to pronounce the whole thing. You say gives us, and then you write your product. So it's that simple. For example, let's say we write hydrogen reacts with oxygen, or you can simply say hydrogen plus oxygen. Don't say arrow, say gives us water. Okay, so hydrogen plus oxygen gives us water, or hydrogen reacts with oxygen to give us water. That's how word equation goes. Word equations are the simplest form, and we use the naming part. We have
Mhm.
already studied a lot about the naming part. If it's left, we're going to uh, complete it in these two chapters. Don't worry about that. And the next one are chemical equations. Chemical equations itself are actually symbol equations. Symbol equation means that we're going to write anything in chemical symbols, be it an atom or a molecule, ionic compound, covalent compound, it really does not matter. We need to write them in those equations. Then there are a couple of things that come along with it. We need to balance those equations. Number of atoms on the left of your equation, which means on the reactant part, and number of atoms on the right of your equation, which means the product part should be equal. That's what balancing means. Also, we tend to use state symbols. State symbols are the symbols that we use to represent their state, and that's written right next to it. So I'm going to pick this exact equation and I'm going to write it over here. Hydrogen is present in the form of hydrogen gas, H2, and oxygen is present in the form of oxygen gas. They both react to give water, which is H2O, right? So
Yeah.
when we write this equation, if you take a look at it, on your left, you have two atoms of hydrogen. On your right, you have two atoms of hydrogen in water. On your left, you have two atoms of oxygen in oxygen gas. On your right, you have just one atom of oxygen in water. So you
Mhm.
multiply the whole thing by two. Remember, you can never change the subscript yourself, or you can never alter the formula. However, you can change the number written on the left of the formula or before the formula, which makes the whole thing as two molecules of two atoms of oxygen. But as soon as we write two, you can see two twos are four for this hydrogen. So we need to balance hydrogen again. So we write two over here. These numbers are the balancing numbers. We can always change these numbers. We can put them in such a way that we can balance the equations. That was too rough. Don't worry. I'm actually going to teach you how to balance equations properly if you don't know that already. If you know that, we can skip that part. Don't forget, I was talking about the state symbols. There are four state symbols. So solids are usually represented as S, small s. Liquids are usually represented as small l. Gases are usually represented as small g. And finally, aqueous solutions or solutions in water are represented as AQ, right? Because we're going to use a lot of things that we're going to use as solutions in water. So actually, this is hydrogen gas reacting with oxygen gas, producing liquid water. That's how state symbols work.
Mhm.
Now, state symbols are usually a part of the question for whichever state symbols that you already know, you're familiar with. They'll ask you to write them by yourself, but you can't really be familiar with the state symbol of every chemical on the planet. There are like billions of them. So, whichever one is unknown to you, don't worry. The hint would be given in the question. They'll mention it as a gas, liquid, or solid in the question, so you would know. If they don't mention it, gas, liquid, and solid, and they use some other English word, take the hint. For example, they say, you took a piece of. Now, you can't take a piece of a gas. You can't take a piece of a liquid either.
Got it.
It must be a solid, right? So, there
Mhm.
would be a hint whether hidden is in those words in grammar or in English, whether written clearly as a gas or as a solution in water, whatever that is, he will tell you. So that's the end of the examiner. So do not worry. You can't really know everything on the planet. No one does. Even I don't. So these things will be catered by the examiner in a very balanced way. You'll never find him unfair. He will always leave a hint. Okay.
Yeah.
Water can exist in different forms. Water in its original room temperature form is a liquid. We can heat water up, we can boil it, it would become steam, which is gas. So if that happens, he may give you a hint. For example, he tells you this water was present at 300 degrees centigrade. Now you obviously already know that at 100 degrees centigrade, water starts to boil. So this 300 degrees centigrade makes sense. You need to write D, not L,
Mm-hmm.
right? Because it could be a gas. At 300 centigrade, all the water would boil into a gas. It would all become steam. So this should make sense. And there would always be a hint in the papers. Don't worry, this was too difficult of a thing. You won't face much of it. So example of balanced equation is, now the book is going to explain the numbers and the balancing part. Uh, I'm a little unsure whether we did the balancing before or not. Did we?
So we started with it, but we did not complete it entirely.
Okay. So when you see this equation, does it make sense to you?
Which one?
The one on the top,
Mm-hmm.
there's only one equation in the first half of the page. This one at the bottom is a little bit more difficult. So let's start one with the easier one on top.
Okay. Okay. Yeah, it makes sense.
I hope you understand that we have two water hydrogen over here and we have two chlorine over here. So in order to balance it, we put this two over here. As soon as we
Yeah.
do, we balance both hydrogen and chlorine at the same time.
Mm-hmm. Yeah.
These are known as coefficients. This two is actually the coefficient. And the subscripts are numbers which actually represent the atoms in the formula. You can't really touch the subscript. You cannot change the subscript whatsoever. So keep that as a simple uh, rule in your mind. There is another chemical equation, this one. This one is pretty simple and straightforward. There are two chlorine atoms on your right, so you write a 2 before the Cl, so in order to balance it.
Mm-hmm.
Okay, and then
Yeah.
comes this equation. Now you can see hydrogen, two hydrogen over here, two over here. So there are four hydrogens. There are two sulfur. There are seven plus one, eight oxygen atoms. There was H2SO4 over here. As soon as we wrote two, two twos are four, so four hydrogen. Two ones are two, so two sulfur. This is four hydrogen, two sulfur, and eight oxygen over here. And here we have a total of four hydrogen plus two sulfur plus eight oxygen. So it's balanced. You can
Mm-hmm.
write it like that. Up top, it would definitely help you how this works. Remember, a number written in the left of it actually affects anything written after it. So this 2 is multiplied by 2 for hydrogen. So we have 4 hydrogen. This 2 is multiplied with S. This S is definitely 1. That's why we never wrote anything over here. So 2 into 1 is equal to 2, which means 2 sulfur, and 2 into 4, which means 8 oxygen. That's how it works.
Mm-hmm.
Okay. I
Yeah.
hope since you understand this, let's go with something more difficult. Okay. What would the brackets mean? Now, if I write a 2 over here, can you tell me how many lead ions, how many lead atoms, nitrogen atoms, and oxygen atoms are in there after writing the 2? What does the 2 mean?
It's for the entire bracket?
It's
Oh
for
no.
the entire formula before
Oh,
the bracket and including the bracket.
okay.
Okay, if you're asking about this 2 is for the entire formula. If you're asking about this 2 is only for the bracket.
Oh yeah, I was asking with this one.
Okay? That's why I explained you need to know about both tools, how both of them work. So how many lead atoms do you have right there?
Two.
Good. How many nitrogen atoms?
Nitrogen 2.
No, these were supposed to be multiplied. Okay, so there is one. So you're gonna multiply this two with this one and with this two. The overall answer is
4.
four. Perfect. If you do the same with oxygen, what would be the answer to oxygen?
Okay, so it'll be 2 into 3 into 2. 2 threes are
Perfect.
6. 6 into 2 is 12.
12. There you go. Now you're doing it in a great way. I hope you get the point, right? Now he explained H2SO4 in a diagrammatic form, and this really helps students to calculate it. So every yellow right there is sulfur, every red right there is oxygen, every white right there is hydrogen. So you really know. So if
Mhm.
I was saying that there are a total of four hydrogen, you can see it right in front of yourself. If I was saying there are a total of two sulfur, you can see that and you can even count that. And lastly, if you count all the red, you'll come to know that there are actually eight oxygen. Make sense?
Yeah.
So these diagrams make a lot of sense for students who cannot really imagine it well. Diagrams help them to cover this difficult part. So balancing the equation. Okay, this is methane. I'm gonna write this equation over here. You have these diagrams, it's gonna really help you a lot. So methane is CH4, as you can see, one big black ball and four small white balls, CH4. That black is carbon, that white is hydrogen, and then there is oxygen O2, and then it gives us carbon dioxide, and then it gives us water H2O. But this equation is definitely not balanced. You need to balance this equation.
Yeah.
Okay. Now, no, none of the books are going to give the hints that I'm about to tell you, but these hints are going to really help you with balancing the equation. So I'm going to give you a set of rules. All right. And I'm going to keep it really simple, small, and straightforward. Rule number one, don't alter formulae. You can't really change the formula you wish to or subscript especially. So don't touch the subscript. If you want to balance it by writing P over here, no, it does not work that way. That's what rule number one means. Okay. You can't write anything in between. I write 5 over here, so I balance hydrogen. No, it doesn't work like that. You can't really change the formula. All right. This is what rule number one means. Rule number two, balance oxygen and hydrogen in the end, or balance elements divided in multiple species last. ओके, या तो आपने हाइड्रोजन और ऑक्सीजन को वैसे ही एंड में बैलेंस करना है, बाकी एलिमेंट्स को पहले बैलेंस करना है, या फिर वो स्पीसीज जो मल्टीपल जो ना वो एलिमेंट जो मल्टीपल स्पीसीज में डिवाइड हुआ हो उसे एंड पर बैलेंस करना है. Okay, so I'm going to write, go with this equation and I'm going to use a different color. नोटिस करें कि आपके पास यहाँ पर कार्बन एक स्थिति में, यहाँ पर भी कार्बन एक स्थिति में. आप इसे पहले बैलेंस कर सकते हैं. हाइड्रोजन यहाँ एक स्थिति में, यहाँ भी एक स्थिति में, आप इसे पहले बैलेंस कर सकते हैं. नोटिस करें ऑक्सीजन यहाँ एक स्थिति में है, लेकिन यहाँ कार्बन डाइऑक्साइड में भी ऑक्सीजन है, वाटर में भी ऑक्सीजन है. दिस इज व्हाट दिस पॉइंट मीन. ऑक्सीजन को आपने एंड पे ही बैलेंस करना है. पहले आपके कार्बन और हाइड्रोजन पूरे बैलेंस होंगे तो फिर ऑक्सीजन बैलेंस करना है. अगर आपने ऑक्सीजन पहले टच कर दिया, the equation will become a lot more difficult for you. There are too many chances of errors and it would take too long. Get the point? So these
Yeah.
are two very simple and straightforward rules. And these rules are going to help a lot with balancing. So let me just erase that. Okay, go ahead with the equation. Try balancing carbon first. Or do you think carbon is already balanced on left and right of the equation?
Here we have one, and here also we have one.
That's right. Good. On the left of the equation, you have one carbon,
So, sir, it's balanced.
and on the right of the equation, you have another carbon. Yes, it's balanced.
Okay, now we'll do hydrogen, right?
Now we'll do hydrogen.
Sir, we'll just on the on the right side, we'll just add two, so it'll be
Perfect.
2 4 then.
Very
Yeah.
good. 2 to the 4. You've already balanced hydrogen. So now is the right time to balance oxygen.
Okay. So here we have two, and here also we have two.
No, on the right hand side of the equation, there are two species that contain oxygen, sorry, not hydrogen, oxygen.
Oh
Let's
yeah, yeah.
add
Okay.
them.
Okay, so we here we have four.
Yeah, on the
So
right of the equation, you have four oxygen atoms. On the left of the equation, you just have two.
we'll just add two then on the left side.
Right. We multiply it by two and we get our answer. Now, let's keep this answer right over here and let's go with this. Notice two oxygen molecules because we have written a two over here, two water molecules because we have written a two over here, and there you go, you have the balanced equation. All right. So,
Yeah.
yeah, this book tells you that. Thank God, I've never seen this statement written in Cambridge. That's great. So work across the equation from left to right, checking one element after another, except if an element appears in several places, leave the element. That's my second rule. Okay? It would automatically get sorted itself out. If you have a group of atoms like sulfate, for which is unchanged from one side of the equation to the other, there is no reason you can't count it up like a whole group. So you can work in groups as well. Don't individually work with sulfurs and oxygens. It saves time. For example, you have a complete sulfate ion over here and a complete sulfate over here. It works like a chart. Balance the whole thing over here with the whole thing over here. Do not work with numbers. Do not work separately, balance sulfur and sulfur, oxygen and oxygen. That might save you a lot of time. Check everything at the end and make sure you haven't changed something that you have already counted. This is important as a recheck.
Mm,
Okay. Now,
yeah.
since you already understand all of this, that's the race. Let's go with example number one. You have an equation right over here. Go ahead and try to balance it.
So we'll first start with zinc, right?
Right.
So on the both sides, I think zinc is balanced.
Zinc is balanced. Perfect. Moving on.
Okay. Mm, Now chlorine, right?
Mm-hmm.
So here we have two, and we have one over here. If we add two over here, so we'll have two chlorine. So we'll on the left side, HCl will at the starting of that we'll add two.
Two. Perfect. Now, since chlorine is balanced, let's move on to hydrogen.
Okay, so on the left side we have two hydrogens.
Mm-hmm.
On the right, right side also we have two,
Perfect.
right?
So it's already balanced. Since we were trying to balance it, so in attempting balancing of chlorine, we automatically balanced hydrogen. So that's great. Okay. All right, moving on. Since you have done it perfectly and you see the same equation over here, Hint, this is really important. You must never change a formula when balancing an equation. All you're allowed to do is to write big numbers in the front of the formula. That's about it. Never change the subscript. That was my rule number one. Yeah. Okay, that's great. Go with this equation. I'm going to write this equation over here. So it's C2H6 plus O2. I leave ample space to the left of it that you can easily write numbers. I'm going to allow you to annotate. So CO2 plus H2O. There you go. If intentionally or unintentionally you write a wrong number, you can simply cut it and overwrite it with the correct number. You can always do that, remember. And then finally, you can rewrite the whole equation clearly.
All right.
Hmm. Remember, oxygen is divided into two species, so we'll keep oxygen for last. And you can try for carbon and hydrogen first.
It's right done.
So, and read it out loud.
Okay. So first, I started with carbon. So then
Mm-hmm.
on the right side, we have uh we have one carbon, right?
Right. Just
And
tell me
on
the
the
numbers that you put. That's fine.
okay, so here I put two. Yeah.
Two CO2. All right. What about
And
others?
then I put three in front of hydrogen. Yeah, here.
Water.
Oh yeah,
Three in front
water.
of water. Right.
And
Obviously, you need to balance this oxygen. And here comes the tricky part.
okay, here we have two oxygen on the right side. Here we have four, and here we have three. So if we combine them, four. So here in total we have seven. Oh, sir, I got it. Seven.
Seven oxygens. So how do we balance seven oxygen with the one on the left?
Sir, we can put seven. So
Seven
seven
twos are
and
14. That would be
14.
14 oxygen over here. That would change everything.
Yes. So when we add this, then on the on the right side, uh,
Okay, let me clarify you with something. Let's see what we have in the book over here. Now they have done this whole seven thing and they have given you two different equations. Let me clarify. Okay, if I write three and a half over here, three and a half into two is equal to seven. So that balances the whole thing. I can also write it like this, plus 3.5. Zero point 0.5 is the only decimal or half is the only fraction that you are allowed to write. You cannot write any fraction. You cannot not write any number in points. You can't write zero point 0.2, zero point 0.3, zero point 0.7, zero point 0.8, just 0.5 and the whole numbers. So this is 3H2O. Or otherwise, what you can do, since you have a half or a point 0.5 over here, you can multiply the whole equation by 2. It would convert the whole equation into whole numbers. So the equation would become C2H6, and you can put 7O2 like you wanted to in the very start. If you want to put 7 over here, you have to multiply the rest of the numbers with 2. So 2 twos are 4, so we need to put 4CO2, and 3 twos are 6, we need to put 6H2O. There you go. This is the balanced equation with whole numbers. Sorry. And this is the sorry. And this is the balanced equation with decimals. Actually, all three of these equations are acceptable and marked as correct,
Mm-hmm.
as shown in the later part of your book too. Okay, are we
So,
good?
yeah, so is it fine if we go with the last method?
It's perfect whether you pick the first one, second one, third one. It's totally up to the student. If you want to fill it up with whole numbers, you can. If you want to fill it up with a half fraction or decimal point 0.5, you're allowed to. You're allowed to do it in any way. Take a look over here. The book clearly tells you you can write this, or you can double everything to get rid of the half, or you can write this. It's totally up to you.
Mm-hmm.
In
All right.
fact, it is acceptable to have half in an equation, but you don't come across them in IGCSE. You can put the half over there, or you can double everything or put the whole numbers. It's entirely up to you. All right?
Yeah.
Are we good? Okay. The book ends balancing of equation over here, but I won't. I will give you some more difficult equations to solve as a homework. You'll get the homework right after the class. I'll send you a WhatsApp picture. Try them at home. They will consist of some bigger numbers.
Yeah. All
Numbers
right.
like these, 7, 4, 6, bigger numbers. Okay, so state symbols I taught you before about solid, liquid, gas, and aqueous solution or solution in water. Now you know. Okay, so
Yeah.
now you clearly know about the equation. Now, I hope you remember and you understand that we have studied the third type. So I have converted the equation, or your book will, into word equations or simple equations. Symbols are balanced and they have state symbols. And the third one you're going to follow in the next unit are ionic equations.
Mm-hmm.
And you're already familiar how to go with ionic equation, write the ions, take or cross out the spectator ions, and then finally get your equation. So these are the type of equations that you come across in the first two units, and you should be good with them.
Yeah.
Okay.
Mm-hmm.
All right. So moving on, how much of each substance reacts in a chemical reaction? So let's take a chemical reaction for an example and understand about reacting. Okay. But before I go with this, one small quick hint. Water is a liquid. You can't write water as aqueous solution. Aqueous solution is when something is dissolved in water. You can't expect to write this as aqueous solution. This is aqua itself. Aqua means water. Okay, so this would be wrong. Water would be like this. Okay. If he says in question ice, water would become this. If he says in question steam, water would become this. All right.
Mm-hmm.
So if he uses other words, other state symbols, be ready to put them as he wants to. He will always leave hints in question. I hope you get the point. So
Yeah.
coming back to the equation we were, how would you know which proportions to mix them in? You can't just keep mixing equal masses. Iron and sulfur do not weigh the same. Iron atoms contain more protons and neutrons than sulfur atoms. So iron atom is 1 and 3 times heavier than a sulfur atom. You can't actually mix them in the way that you want to. So you need to know about the masses of atoms in order to understand how much of every element or species is going to participate in a reaction. In order to clear up masses, Let's start with relative atomic mass. We have studied that previously in chapter 3 about isotopes and their abundances. Let's take a closer look at relative atomic mass and understand what it is. Now, before I move any further, there are a few things as a prerequisite that we need to explain. First things first, atoms are amazingly small. They're so small you can't even see them with a naked eye. They're so small that the microscopes you have been using in your biology lab, such as compound microscope or electron microscope. Now, I do understand electron microscope is used to view bacteria or even viruses, but you can't really view atoms with it. So atoms are very small, even smaller than what we have discussed about bacteria and viruses. And when it comes to masses, you don't have any balance in the world to measure single atoms or their masses. For example,
Mhm.
mass of hydrogen atom is about this many grams. Now, which balance is going to cover this many zeros? Obviously, no balance. You can see there are so many zeros. This negative 24 gives you a closer idea of how many zeros there are.
Mhm.
So, what do? We don't get with the difficulty. We use a relative scale. Relative scale is a very easier scale. Now, remember, humans are extremely sharp. Humans are very good. They are intelligent species. When they can't measure anything, they stop measuring and they start comparing. For example, I take any three students of your class and stand them at a place right in front of you. Let's say I take three girls and I ask them to stand right next to one another as A, B, and C. If I don't allow you to go near the girls, if I don't allow you to touch them, if I don't allow you to use any instrument or measurement technique, can you tell me the height of any individual girl? Of course not, right? I never allowed you to use any instrument. I never allowed you to touch them. I never allowed you to move them. You can't really measure them. But even when you're sitting at your seat in the class, and let's suppose your seat is at the very end of the class, even from there, if I ask you who is taller among all of these or who is shorter among all of these, you can easily tell me, right? You can
Yeah.
always easily compare A and B or B or C. You can imagine different girls from your class right here and now, and you can think about them, which one is taller and which one is shorter. You hardly take a second to judge, and you will be mostly correct, right?
Yeah.
Now, if I make B as a standard, and I ask you to compare everyone with B, you can easily tell me if A is shorter or taller than B, and you can compare C and you can tell me whether C is shorter or taller than B, right?
Mhm.
So, can we do the same with masses? Yeah, we can. Instead of measuring individuals, what do? We start comparing them, and comparing is what we consider with the word relative. Relative is a very good way. What we do, and he said the exact same thing, we take masses of atoms and molecules, bigger stuff, so that we can even weigh them in a balance, and we start comparing them with the mass of atom of carbon 12 isotope. This is our standard. This is like B. I chose B as the standard. Humans have chosen carbon 12 isotope as the standard. Everything they compare with carbon 12. And they instantly come to know whether it's heavier than carbon 12 or it's lighter than carbon 12, right? Easy enough.
Mhm. Yeah.
Okay. So if I change all of this and if I drag you, is the periodic table chapter behind this one or ahead of this one?
Behind this one.
Uh, yeah, I guess we have left it behind in the previous chapter. So I'm gonna go a little bit back. This is not exactly the periodic table I want. This is the one that I want. No, this one doesn't even have the masses. Well, even if it does not have the masses, you clearly have an idea if you look at the periodic table with the masses that anything that comes after carbon, this one is carbon right here, anything after carbon is heavier than carbon, anything before carbon is lighter than carbon. I hope you already know that because of the
Yeah.
mass numbers.
Yeah.
Mass numbers, they are usually written right next to the elements, so you would know. I really can't find a periodic table over here that consists of atomic and mass numbers, unfortunately. Okay, so coming back to the page where we were, so you would know, we call this carbon 12 scale. On this scale, one atom of carbon 12 isotope weighs exactly 12 units. Most common hydrogen isotope is 1 unit. And these are much simpler numbers to use. Imagine if you had to use this number, this whole big negative number. And imagine you have to use 1 and 12 and simpler numbers like this. So if you have a copy of periodic table with you that gives you the math numbers, you'll see very easy math numbers over there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Numbers which are really easy to work with. You will hardly find a few ones with decimals. The rest all are whole numbers usually.
Yeah.
All right. For example, he tells you in the extension work that we use approximations. Accurately, hydrogen is 1.008, but on carbon 12 scale, we use 1 to keep it easy, to keep it simple. So you're going to use whole numbers. Don't worry about that. So the basic unit on carbon 12 scale is 1/12 of the mass of carbon 12 atom. This is approximately the mass of most common hydrogen atom. Fluorine 19 will have the relative mass of 19 because it's 19 times that of 1/12 of carbon 12 or hydrogen. Magnesium would be 24 because it has a mass of 24. The masses we are talking about are individual isotopes. But when we look at element, we actually combine all those natural isotopes. We take an average, and that's how we define it. Now, this is the definition right here. So, relative atomic mass or AR, what we do is with the element is we take a weighted average of all the isotopes of the element, natural ones at least, and we measure them on a scale of carbon 12, in which carbon has exactly a mass of 12. So we compare them with the carbon 12 scale. How do we work with this? On the scale, the mass of fluorine is 35.45, but we round it off to 35.5. Or copper has a different number, we round it off to 63.5. Or sodium as 23, we work with that.
Mm-hmm.
Remember, in order to work out the average, you must know how much is present in each sample. I don't think that's a part of your book. That isn't, so we really need not worry about AR. Okay? I hope you haven't calculated AR in any of the previous chapters, have you? Let me just quickly take a look. No, I don't think you did. Yes, you did. There you go. Do you remember this method of calculating AR? That's why I
Oh
was.
yeah. Yeah. I remember this one.
So this is how we calculate AR. We tell you the percentage abundance, relative abundance of one of those, whether it's mass, and the abundance of the second one, whether it's mass. What you do is that you multiply the abundance with the masses, you add them all, and you divide them with 100 because you consider 100 atoms at a time. You get a number that is your relative atomic mass or AR. So you already know how to calculate AR. That's why the method is not explained at that point because they have done it previously. Are we good?
Yeah.
Great. If you understand this, let's go back to where we were. So let's directly jump to formula math.